18th, and we're very happy to have him talk about parallelism part 2.
Thank you very much. I'm glad to be here. Glad you're all here. I'm here to talk about, basically extend on what Johnny talked about yesterday. He was doing MPI parallelism. I'm going to talk a little bit on other forms of parallelism, including, here we go, conveniently parallel. I like to, some people call this embarrassingly parallel. I like to call it conveniently parallel because, well, anyway, you can imagine if you have work units that are can be processed concurrently, such as image format conversion, converting PostScript files to PNG to be placed on the web, transferring numerous files from here and there. All these things can happen independently. The MD5 checksum example is I work a lot at Goddard and also here at Ames, and if I need to compare two files, I don't want to transfer a giant file just so I can run a compare command on it. I can do the checksum on both places and then just compare the checksum. If I have multiple of those files on each coast, then I can run them in parallel and just compare the checksums from each file. Renaming files, matching a particular pattern, and also the MapReduce algorithm, which is often used, which is used by the, web search companies for delivering output from your web searches to you. Another NASA mission, the Kepler mission, has a satellite up there continuously monitoring over 100,000 stars, and the information it gathers is star brightness, and it has an algorithm for computing, to figuring out if there's a planet orbiting that star based on the brightness changes. And we'll go into a little bit of detail on how they process that all 100,000 stars at the same time or very closely. Long wavelength radiation physics in an atmospheric GCM. You saw some output from the GEOS-5 model and the ECHO model. Those models have radiation physics. Basically takes solar radiation from the sun and it heats up the atmosphere and the ground, but also at night the long wavelength, everything above absolute zero radiates in black bodies, so they have a long wavelength parameterization that must run, and since everything's above absolute zero, all the grid cells have to run that package. That is conveniently parallel. And also another thing that comes up often in well, I won't say graduate studies, but I do know of a particular person at Goddard who was tasked with doing a parameter sweep of a numerical algorithm to explore the parameter space and to see what its sensitivities are to various tunable knobs that are always in these things. You're never solving the exact problem. You always have knobs to turn, and so that the output can be tuned to reality. And I'll show you how to go about doing that in parallel. Some approaches, shell commands, command lines like for each and wait. If you're familiar with the C shell or the TC shell, these are available under that, and I believe they're available in some of the other shells as well, but I'll talk about the for each and wait. Perl has a fork utility where you can spawn child processes, and they are independent processes that go along with the parent, and they can do separate work, and then they come together at the end. Make -j. Make is often used in, let's say, in the Unix world to build codes. It takes commands. Well, I won't get into that too much. Xargs -p. You can also run parallel processes, and then there's the GNU parallel utility itself. And this website gives a very nice rundown of some of these options, some of these approaches, some of their pros and cons, and basically it's going to tell you that GNU parallel is perfect. And it has a lot of nice features. Unfortunately, it has a huge number of features, so you can get lost in that very quickly. OpenMP, I don't know if you've been told much about that, but it's a way of doing parallel processing on a node. using shared memory for communication, MPI, which Johnny went over yesterday, and combinations of all these are possible. It all depends on what problem you're trying to solve to be, which one is the best approach. Let's say we want to convert a bunch of PostScript files to PNG using at most 12 processes. So we don't want to overload a node, so we want to have a little block in here. What we have is a counter. The N counter, we initialize it to 1. The set command looks for files ending in .ps. The star is a wildcard. This is ls minus 1, so we have output from the ls command one line at a time. And that's saved into the files variable. And for each of those files, we create a file placeholder. And the file placeholder will take on successively each value that's in the files variable. And first thing we do is check our counter, and if we're over 12 or over, we wait, reset the counter, and then end if, but we're not there yet. The next command is we're creating a placeholder for the new name. And basically we're stripping off, this strips off the .ps and saves the base name. Then we use the convert command, which is available if you have the module, the ImageMagick module on Pleiades loaded. So we convert the original file .ps into .name PNG, and the ampersand is the key here. Let's see here. The ampersand puts this process in the background and continues going. So now we put that process in the background, we increment our counter, and then we go back up, and once we've launched 12 of these, we're going to wait. And we're going to wait for all those child processes to complete their work, create their new file, and then return. And then we're going to reset our counter and go again. At the very end, we have a wait to just make sure everybody's cleaned up. And then we can, you can either exit out or continue on with the scripting if you have some other processing you want to do. Some drawbacks of this approach: different images may take longer or shorter time to process. So there's a load balance issue. Some of these 12 processes may have a small image or less complex, and they finish very quickly. But this approach does not dole out new work as others finish. So you're going to have some load imbalance and basically wasted time. There is one possible way around that, is you can sort the files initially by size, but that doesn't always. It's an indicator of complexity, but not completely. You can still have issues with wasted cycles. Moving on to the Kepler mission, and they actually use the GNU parallel in their processing. I don't have complete access to their processing, so this is sort of a stripped down version of what I think they do. So they have a serial executable that takes as input a star name. And let's assume that the executable knows what to do with the star name. It knows where to get the input file based on that star name. It knows what output file to create based on that star name. And you can run one at a time and take up a lot of, and that's, of course, for 10,000, 100,000 times, that's going to take quite a while. You can, on a particular node, we can go down here and process 12 concurrently, taking star name, taking the input from a list of star names, and that's just starnames.lst down here. The J tells parallel to launch at most 12 processes at a time. And here we give it the executable name, and then the curly braces on the end are going to be filled in with the star names from the list. Now it will continue processing every file, every star name in the list until they're all done. A nice feature of parallel is it knows about other nodes. You can tell it other nodes to run on, and it will. And this is an example PBS script. Have you been introduced to PBS scripting at all? Not at all. Okay, this is your first one. The the minus L select equals 69. Select 69 chunks of NCPUs equals 8. And the model we're going to use is the Harpertown chip. So we have 69 times 8 processors that we can use, and we're going to use them for 40 minutes. That's the number here. It's hours, hours, minutes, minutes, seconds, seconds. Down here, star names. We tell, let's see, this is an indication of where we want to run the data, run the executable. PPN is processed per node. Since we have, the Harpertowns have only 8 cores per node, we don't want to overload the system. So we tell it how many to launch on each node. And we go down to the parallel command itself, where we have the list of star names, the minus A argument. We're going to launch 8 jobs on each node, and the SSH login command. I believe Johnny went over this PBS node file yesterday, and it has a list of all the node names that are provided when you launch this by PBS, when you launch this command, when you qsub this job. And of course we give it a path to the executable, and the curly braces are filled in, and this will run, presumably this will run 69 times faster than if you did it on one node. And this is of course important if you have 100,000 things you want to do. The parameter sweep example that I went over. Say we have, you've spent all summer, you've written, debugged, optimized an algorithm. Say it's cumulus parameterization that you want to stick into a global circulation model, or some other algorithm, and it has 3 knobs. Those knobs can take on values between, knob 1 can take on values between 1 and 10, and using the sequence command, we're going to create a list of values between 1 and 10 with every half. So there's going to be 19 entries in that first list. The second knob can take on values between the freezing point and boiling point of water. And we're going to create a list every 1 degree for 101 entries. And the third knob can take values 20 to 25. So now we have a total combination of almost 100,000 combinations. We want to run this executable. And just like the Kepler example, we can do that with the parallel command. And of course, this doesn't tell you what to do with all the output. You'll have to post-process that. But this will get you the data that you need to figure out, to fill in the database of possibilities for this particular algorithm. Any questions there? Okay. Alternatively, if code expects named arguments, such as minus K1, minus K2, minus K3 for the knobs, we can create a list of all those entries with this command here, and then pass into a second parallel. So parallel, a sort of a large text file. I don't really like this example, but I'll go through it anyway. This is inspired by the MapReduce algorithm, because instead of one sort command on this giant file, it can be a gigabyte or so of text, we break it up into 1 megabyte chunks, where in this case 1 megabyte is the default size. The record end option specifies, well, like the record end, and is applied when you use the pipe command. The files option tells the output, will tell the parallel command to store the output from the command in separate files using block and then size. Size here is in bytes, and it can take on, it has a suffix. You can do K for kilobytes or P for petabytes. depending on how big your file system is. And I would suggest using a luster stripe size for the size if you use this. Each block is passed to a sort. Output from that sort is saved to a unique file. This pipe over here passes that list of files to another parallel, which does a merge of individual files, and the sort minus m does a sort and a merge. And then the RM here removes intermediate files, and the output is saved into big file.sort. Some drawbacks of this. In the extreme, if you had as many cores as you could possibly think of, and you tried to use all of them, this algorithm would get more and more complex for the second step. And that's really not what MapReduce is all about. It's trying to do all the work into the map, and then the reduce should take very little time. And in this case, if you say you split the file up into one line at a time, you would have one file per line, and then the second sort is going to have to merge all the files anyway. So it's just the added complexity. So, and that's basically what I say here. A real MapReduce is going to, here's an example of a real MapReduce. So say we want to count the number of times a particular pattern, in this case rem size, appears in a text file. You can do that with a single command here. The single grep minus C will give you a count of the number of times this pattern appears in this particular file, and this is just a file I had laying around. It's about a 10 megabyte file. The actual result is 94,078. But this is going to take a long time the larger this file gets. So if we could somehow split it up, count individual files, and then merge the result, it could take less time. And that's what we do here with this command down here. If you're familiar with the cat command, it basically dumps all the contents of a file out to a screen, or in this case, we're piping it through parallel. We're going to split it up. We're going to run 5 jobs. The block size is 2 megabytes in this case. The command we're going to run is grep minus C for this pattern. And then we're going to aggregate all those intermediate results with this awk command. And the tail just prints out the last entry in that from the rest. Any questions about that? And now I'll go on to less than conveniently parallelism. Some work units very often will depend on other work units. In the example yesterday, the pi example, the calculation part of that was conveniently parallel, but the reduction, the final reduction, depended on all those processes being completed, and that depends. Okay, so some work units can take longer to process than others. We went over the image conversion.
You're lost.
Go ahead.
Okay. The solar radiation code in an atmospheric GCM doesn't need to run if the cell is in darkness. So every time step you run, half of your processors are going to sit idle during this routine, unless you do some coding to take care of that, and that's not very convenient to have to code to manage that. It's done, and it helps, especially for radiation packages, because they tend to be very expensive. The people who write these things go to the effort of of just redistributing that work to the idle processors and then transferring it back, just because it's expensive. It's an expensive algorithm. Algorithms that require neighbor communication are less than convenient, because at every time step you have to share information on the boundary between processes. And Johnny went over sends and receives yesterday, and I'll have an example of that later. Atmospheric and ocean dynamics, where you have fluid or other stuff moving from cell to cell. You have to do communication to make sure everything is accounted for and you're not losing either mass or energy or something. Diffusion of heat in a solid is the example I'll go over later, where it requires, if you break the problem up and do parallel processing, you have to share information at every time step in order to get an accurate result. In these situations, less than convenient parallelism, if you want to call it that, load balancing becomes a major concern. Data movement, your communication isn't free. As you saw yesterday, when Johnny had all the processes communicating on one node, it was quite fast. But as soon as you go across node, it slowed down dramatically. And as the job gets larger and larger, you have more and more nodes to communicate, and they get farther and farther apart. The communication becomes a concern. The domain decomposition, and I believe Chris Hensey mentioned this to you, where the global domain, or whatever domain of interest you're running, if it's a land model, you would break up the grid cells and run a set of them on a set of processes. You want to make sure that all of those processes have roughly the same amount of stuff to do. Otherwise, they're going to be waiting. Some processes will be waiting. And you want to minimize communication between those processes. Here's one example of a domain decomposition. This is the cube-sphere grid used in the GEOS 5 cube-sphere model. This is a C60 grid, so each face of the cube, well, I'll go back. Imagine the Earth inside of a cube, a box. And it touches the box at the centers of each face, over here. And then the faces of the cube are mapped onto the surface. And this is what you get. The C60 means that there are 60 cells along the side of each face. And in principle, this could be run on as few as 6 processes, one face per process. But in general, in the GEOS 5 GCM, there's enough work to go around. You can break these faces up into 4 or 8 and run on, say, 24 or 48 processes. Here's a nice illustration. I like this. This is roughly the same grid. It's a little lower resolution than the previous one, but it has real model data overlaid on top. And I want to point out that the model run that generated this was at much higher resolution than the grid shown here. I believe that was probably a 10-kilometer global run that generated these cloud fields. And it also has a nice illustration of how those cells are broken up and run on a computer. In practice, we wouldn't break up each individual cell and have it on a different process. We would have contiguous blocks of processes, and each processor would have a contiguous block. All right, so now since we're talking about domain decomposition and less than convenient parallelism here, we need an example to talk about, and we'll use diffusion in a solid, and we're going to use temperature as the diffusing property. In this equation, and I'm not going to go through the derivation, you can look online. Wikipedia has a nice write-up on this. T is the time, U is the temperature along the x direction in a particular time, and we're only using the 1D refers to the one spatial dimension. K, C sub P, and density are material properties, which we're going to consider to be all equal to 1, just to make it simpler. One approach to solving this differential equation is to approximate the continuous derivatives with finite differences, where temperature and time are discretized. X then becomes a set of equally spaced points in the solution domain. I is the total number of points here. Capital I is the total number of points. I, in times, we loop through the solution. If we replace the time derivative with a forward difference, and I'll talk about that in a little bit, and the space derivative with a central difference, the result is this recurrence relation here. The lag is really... Okay, what we have here is an equation that gives us the temperature at a point I at a future time, n plus 1, given only information at the same point at the current time, plus information at neighboring points at the current time. And let's see, in this case, R is delta T, which is the time step that we're going to use, divided by the spatial, well, the choice gives us a simple solution that's easy to understand and easy to code, actually. But it comes at a cost, and that cost is kind of illustrated here. The stability condition, delta T over delta X squared, has to be less than a half. And practically, this means that if we want to get a higher spatial resolution solution, we would normally shrink the delta X to a minimum that we can, if we have a big computer, we can do a lot. But this relation, this stability condition, requires us to then shrink the time step dramatically to maintain this condition. So the simplicity comes at a computational cost. If we had used a central difference for time, or even a backward difference, it would very dramatically relax the time step condition. We could take much larger time steps and still maintain numerical stability. However, each time step would then cost more because there's some linear algebra involved at every time step. So there's a pros and cons to all these. Even with this simple problem, there's a lot of choices to make. Some points to take away. We're not solving the actual problem. The real problem is continuous in time and space. So we're approximating that with discrete points. The choice of forward difference, as I said, has a stability condition that must be met to get physical results. At every time step, we use the current value and neighboring values to calculate a future value. We must specify the complete solution at the initial time, and the code must store 2 copies of the solution representing the current and future solution. Any questions there? There's a lot of information here. Okay, whiteboard. This is our 1D problem. So we have T1, temperature 1, temperature 2 here. This is our 1D, so I consider it a wire, metal wire, and we want to figure out what the temperature is along that wire at a later time. So this is the continuous problem. We're not solving that. We're going to...
Can you stick us a little bit? We're going to have the whiteboard.
Does that work? Okay, so this is our we're actually going to solve this problem. And so we want to calculate the value of the temperature at this point at this time. So this is so consider this to be the initial solution, and we want to calculate the new one. We'll use information from here, here, and here. And then once we do that across the whole line, we can go up and then just keep going down. For domain decomposition, if we were going to decompose this into multiple processes, the value that we need to the right is going to be on somebody else, is going to belong to somebody else. So we have to, at every time step, we have to update what I like to call a halo point to along with C, to make sure that we have all the information we need to do our calculation. Does that make sense? Now let's talk about 2D. Say this is a bar. We have the cells are our discretization of the continuous bar. We have the solution at the initial time. We specify it as whatever it needs to be. It could be a sine function or just a zero if you wanted to. And the time, the temperature looks like this. T1, T1, and T2. So we want to find out what the temperature is all along this bar. And we have to specify, in this case, we also have to specify boundary conditions up here. Because in order to, well, say this, hold that. So this is T3, T4. In this case, figure out what the temperature is in this cell at the new time. In this case, we need, say it corresponds to this one here, we need information from the nearest neighbors and ourselves, and we can use that information to calculate the new time. And then once we have all the bar done, we go to the next time. Does that all make sense? In that case, okay, I'm going to go through some code.
Dan, how are you going to explain how to do decomposition on the 2D, or is that in the example?
Actually, I can't. Well, it's I have a nice ASCII code here. All right, where is all mine? These boxes here are, consider this area here, the computational domain. It's a section of the bar, section of a 2D bar that's assigned to rank 0. And I wish I had colored these, but this central region here is the computational domain for another rank, and this goes on down to whatever the number of ranks you have. The halo, top and bottom, is the information that must be exchanged at every time step in order to do the calculation we need. this init function here, and I'll give you this code. It'll be made available. This init function here initializes the temperature within the bar at the initial time. This is the meat, if you want to call that. This does the update from old or current, if you want to call it that, to new. In this case, the stopping condition is instead of doing a fixed number of time steps, this particular implementation checks the old versus the new, and once we get down to the difference between those being small enough, and that's specified was one of the arguments, we stop. Presumably this sort of situation reaches a steady state and doesn't change after that. This is our main function, and I won't go through all of this, but we have MPI init, as Johnny mentioned yesterday. So after this point, there are multiple processes running all at the same time, and they will all execute the same set of code. And the only way to get them to not run the same code is test for this P rank. This is the only unique marker that we can use to determine, say, this code right here. If P rank equals 0, this is rank 0. We print out a usage statement. So if the arguments are, if you don't give enough arguments, or if they're the wrong, well, maybe not, it doesn't check that, but if you give 0, if you give the wrong arguments, it will complain. Okay, in this case, we're going to initialize the grid, the NX and NY, to be, since we're only doing the decomposition along the Y dimension, we're going to do the total numbers of Ys divided by P size, which is the number of ranks. And then X is just whatever it is. Now we could, in principle, we could break the bar up in both dimensions, but that would complicate the communication quite a lot. Here we're setting up the initial state of the 2D field. At this barrier, we wait at this barrier, and Johnny went over this yesterday. Everybody has to execute the barrier before anybody can continue. Here's where we figure out who's our neighbor up and down. Rank 0 is only going to have one neighbor on the bottom. The last rank will only have one neighbor on the top, but everybody else has an up and a down that we have to communicate with. Here we're setting the global delta. This is the stopping condition value that we're going to use during the loop to some large value. Here we start the timer, and while global delta, some big number right now, is greater than specified precision, we continue doing this loop. And here we go. Old and current are the same. Well, I should have put this current, but so given the old solution, we want to calculate the new solution. First thing we do is go in here, and if we have a up neighbor, we do a communication. If we have a down neighbor, we do another communication with MPI sends and receives. We do the solution update with the update function, and that gives us back a delta. And now each process does its own portion of the bar and returns its own delta. And here we use the MPI all reduce to gather those individual deltas into a global delta. here we print some diagnostics, iteration count, and the current global delta. And this is the end of the loop. At this point, we basically go back up to the while. We check our global delta against a specified position, and we continue until we've met the goal. Any questions here? Okay. I want to point out that this all reduce is using the max MPI function. Once we've achieved the solution, we stop the timer and we print out some more diagnostics, and then we call finalize to shut everything down. Any questions there? Okay, I'm going to try to get in and actually run this. There's an example of make. It takes this make file here, has some instructions in it. Basically, we're going to create, this is the executable name. This is a library we're going to link against, LMPI, and Johnny went over that yesterday. Probably should go over that too much. Anyway,
Maybe working this without the Q sub, because I don't think Johnny really did much difference.
Okay, Q sub is the interaction, is how you're going to launch jobs with PBS. The I option gives me will give me a list, will give me nodes, compute nodes, but it will also give me back a shell interface so that I can run anything in that set of nodes I want. The V will pass along and make sure that the shell that I get has all the same environment variables that I have now. In particular, if you want to run commands that will launch another window, like xterm, you want to have this so that the Q sub knows what your current screen is. I'll need an hour there. PBS-PL3 is a development platform. It's you get very quick turnaround of jobs, but they can only be 2 hours in length. All right, so we're in our all right. So I didn't specify what I needed. And it did exactly what an X and Y in precision. So we want to do, say, 64 by 64 and 0.001. And we're done. Not too bad. Here you can...
You would ask for one node with 12
I did one with 12.
12 processes?
Yeah.
So this is 12 processes.
Well, actually, I only used 2, but
Oh, the API executives.
yeah. So it prints out, what I have here is I print out the global domain, well, the domain on each process. In this case, the X dimension we're not breaking up, so it's 64 on both processes. And we break the Y dimension up among each process, so each one has 32. So what we can do is say 4 here, and Y is 16 because we use 4 processes. Any questions? You want me to play anything? Anything you want me to try? We can do anything. We have the code.
Yeah, I have a question.
Sure.
You know, some people use Fortran, some people use C to write the API code. Do you know which one is better?
Whatever your preference.
They both access keys about the same speed.
I understand C does some things with strings a lot better than Fortran, but it honestly, I don't know if there's any difference. It's whatever your preference is, whatever your training is, go with it.
So, I mean, if you're developing a code from scratch, it's probably something of a luxury, right? I mean, you've probably got a base of code that you're working with, and it's already in a language. So often the decision is made for you. Or you're in a community, and their code is in something, and you're adding a new package to it. And, I mean, it's not very often you get to actually choose.
One thing I'll go over tomorrow with the frameworks talk. ESMF is a framework within the earth science community for doing a lot of this stuff, like Halo interaction. You don't, for a complex code, you don't want to write your own Halo update code. You want to use a framework. And right now, the ESMF interface is mostly Fortran. There isn't a lot of C interface to it yet. So you're almost stuck with Fortran in that case. So, like you said, sometimes the choice is made for you.
Here's a question from the virtual audience. Edward Fire says, satellite sensor data files are often delivered with file names that cannot be prognostically calculated. For example, VIIRS data file names include the timestamp, but the length of the granule is variable, making it impossible to predict what the file name will be. Once the file name is known, the time can be parsed out, but the file name must be acquired first. In searching a large archive, a find command to search is very slow. What can be done to make this faster?
On a parallel file system, well, the GNU Parallel website has an example of doing parallel find. Having separate cores interact with the file system to do that, to perform that action in parallel.
So Edward is replying that. He says, thanks, I'll check that out.
That's all I had, unless there are any other questions.
Can you just go through the key stuff again?
Sure. Do you have a specific question on, well, for instance, the PBS script that I had earlier? Where is that?
So I think one key thing here is recall that there's, and Q sub is the way you get ownership for a period of time. Okay? So you're submitting a job, either a script or a job that's actually interactive. And what Q sub is doing is it's putting your request in a queue, and PBS, this resource allocation manager, goes through all the requests and says, okay, I'm going to honor this one next, and I'm going to allocate it the resources that it's requesting when they're available, and when they're available, they're assigned to you or your job, and then you have them, and you can use them either with a script or with an interactive session like Dan was doing. So I think that's the key. So in order to actually get compute resources, you're doing the QSUB, and then what resources you actually get depend on the options that you put on the QSUB. For example, Dan was requesting one node of a specific type. Basically.
Right, and in this PBS example, this is a text file that contains these PBS commands. PBS understands this hash PBS. In this case, the -L select, we're getting 69 nodes of 8 cores each, and I had something similar when I did my interactive session. We're asking for wall time equal 40 minutes here. Now, a lot of times you don't know how long your job is going to take, so there's going to be some iteration on how much wall time you request. Different queues have different limits on what they will accept. Right here, the normal queue, I believe, has an 8-hour wall limit. You can ask for as many CPUs as you want, I believe, in the normal.
I believe that's right. I mean, up to however many there are on the floor.
Sure.
You ask for a lot, and you'll probably end up waiting a long time, and your job may have to sort of be scheduled by hand by the operators.
Right. So there's a balancing act of what you want and what you can get, and you have to play nice with the other people on the system. Okay.
What's the difference between the QSUB and adding a n node, a letter at the end of the command line?
A letter at the end of the command line. I'm not sure what you
Oh,
mean.
the ampersand?
Yeah.
So the difference between QSUB and the ampersand.
Okay. The ampersand will only work interactively. For instance, if you have, if you're on one of the PBS login PFEs, you can use the ampersand, but I'm not advocating that, because if you use too much wall time, they'll complain. The ampersand will launch whatever process you specify in a background process on that node, and you cannot run on different nodes.
Is that is number sign a prompt? Or is that a comment?
Number sign is how you reference environment variables in your shell. So $arglist and $workdir are environment variables that we set right here. You set env.
I'm sorry, he's talking about the # PBS stuff.
Yeah, the pound PBS. Are these shell commands, or is this a script? Or
This right here,
those aren't comments, are they?
no. This right here, all of this sort of purple text here is in a text file, and QSUB understands what #PBS is. It understands this as information that it needs to schedule the job.
Oh, okay.
Is it a pre-processing hash code?
QSUB is looking for it. So
So it is a comment character if you run this in a shell, right?
Yeah.
So those would be treated as comments, but there's this this thing where you could pass a straight shell script to PBS, and it will run the shell script, but you can put these directives in to PBS, to the QSUB, and save yourself some typing on the QSUB line itself.
Okay.
But they're done as comments so that you could also just run this script in a shell if you have resources appropriate to do that.
So, so far when we've been running things, it's been on actual pleas, right? But if we had a large program, we'd be doing it on Sandbox and plugin.
are you talking about the NEX.
Sandbox?
Yeah, I remember.
So I think it's almost reversed. I think you'd probably do a lot of the development on the sandbox, and then when you wanted to run big, you would run on Pleiades. But
Yeah.
you're welcome to do the development on Pleiades as well. It's just it may not be as convenient if you end up waiting for resources to be allocated to you. So the sandbox may have sort of shorter lines to wait for resources.
The accounting is a little different too, isn't it? And Pleiades and-
I don't know how the sandbox accounting works. I wouldn't be surprised if it's different.
So in other words, Pleiades, standard billable units, or standardized billable are allocated to PIs and to groups. So NEX has a certain number of SEUs for all the people working with NEX. And so that is a limited resource. Right now we're not pumping up near the top, but when we have a lot of new users and we don't know yet, as beginners, we don't know yet how much time we're going to be taking, how many billable units we're going to be consuming. It's probably better to start, experimenting on the sandbox and getting some understanding of that before moving to Pleiades. But some of these small programs and examples and things are probably just fine to run on Pleiades because we don't need to consume them.
That's right. Yes. And some of the work you might be able to do on a front end. You can't do MPI runs on the front end, but you could do editing. If you were doing OpenMP, you could do that on the front end as long as they're short runs and you're not using too much resource. But the MPI, I think, is prohibited. Basically, if the command doesn't exist on MPI exec doesn't exist on the front end.
There are ways around that, but yeah.
So, in terms of running model, when should we use the MPI programs?
And that would be in your PBS script itself. Down here you'd have, instead of this parallel here, you would have MPI exec, whatever executable you're running, and then you'd exit out.
So I think Edward Tyler had another question. Let's see. So it says, GNU parallel examples generally omit options like number of processors. Does GNU parallel make good guesses about system resources?
That's a good question. I do not know.
So was everybody able to log on when you finished with Johnny? Or some of you able to log on, do the pass-through, all that stuff?
Mm-hmm.
So
Let's just see a show of hands how many are can now log on to SPF.
Not with a pass-through, though.
At lunch tomorrow, I think we can try to we'll get somebody after lunch. Steve Eastman, who's going to be talking to you in the afternoon, and he can help walk you through those other issues.
Okay.
But if you're able to log on, and everybody is, even if you don't have pass-through, you should be trying some of this stuff. And Dan can point you with the heat code. You can look at that. You can try the Pi code that Johnny did yesterday, or the Hello World code. You can be trying these things. Make sure you understand compilation, you understand the QSub, you understand the MPI execs. Just play with it. See how it works.
So Johnny, in his handout, showed us where the example code is, and it's also now on the NEX portal for those not in the room who might be able to run it somewhere else, and or are on Pleiades. But what about your code, Dan? Is that?
I'll have to put up I'll have to create a tarball and give it to you, or put it someplace on Pleiades and send out an email.
Yeah, probably on Pleiades.
Okay.
Yeah, tell people where it is. Okay.
The other thing I wanted to say is you haven't been introduced to them, but there's actually a scientific consulting staff here. They're expecting questions from you all. And if you have, generally the way to get help on our system is to, let's see, probably the best way is to call the help desk, and they can forward the call
Supported
to a
now.
scientific consultant if it's during normal business hours. They may be able to answer the question themselves, so they have a lot of experience. But if they don't, then they'll escalate it to second tier, which is the scientific consulting staff. When you're actually doing work next week on projects, we'll try to have somebody wherever you are. Is that going to be here, Jennifer?
Yeah, we're going to be actually spreading out in
Okay, so we probably have a designated place in this building for a scientific consultant to hang out to answer questions. I'm not sure if questions would be answered at night if Johnny's reading email. So one way to do this is probably just to send mail to SciCon, SCICON, at nas.nasa.gov. So SciCon at nas.nasa.gov. And that'll automatically go to the group of scientific consultants. If you actually had an issue other than just a question or something like that that you thought you needed resolution to, then you could formally create a ticket and
Support at
probably
NAS.
support at NASA
Yeah.
would be the best way to do that. The control room is at phone number 650-604-4444. If it's from an extension in the building, it would just be 5 fours, 44444. And there's an 800 number, but I don't remember what it is. Did Johnny point out the knowledge base too when he had you this afternoon?
He did point to the webpage.
Oh, okay. The HEC webpage, yeah.
.gov and
HECC,
HECC.
KB. Okay. That would have the 800 number if you're calling from a cell phone.
I believe it's 331 user, 1-800-331-user.
I'm sorry?
1-800-331-user.
Oh, that could be it.
I think that's it.
It also looks like there's a lot of how-to pages.
There's a huge number of how-to pages out there. There's a search facility in the knowledge base, so you can sort of ask a question and it'll probably direct you to a page that's close to what you need. So try that out, but there's also people backing that up if you have questions. So.
I see Miles is asking for the code, and we will post the code later tonight. All right, break.